So, how did you end up kind of getting into this space or, discovering kind of the use of ultrasonic energy versus heat energy, and what unique challenges did that alternative path present to you?
Yeah. So I have to be honest, when I got in additive manufacturing, I didn't really know what I was getting into. It sounded very cool. I completed my bachelor's degree in India in mechanical engineering, worked in India for 2 years, and then came to the US for my master's degree. I wanted to get some exposure to research, so I approached my advisor, Professor Keng Shu, at Arizona State University, and I just asked him if he had any projects I could work on in his lab. At that time, he had an idea of using.
Hello, everyone. Welcome back to the It's Material podcast. I'm your host, Puneeth, and joining me today is my co-host, David. David, how's it going?
Pretty good. Yeah, not much to update. It's only been 1 day for us, from the
Yeah.
last one, so nothing
We're
really has
trying to get
happened.
ahead. Yeah, we're trying to get
Yeah.
ahead for you guys, considering I'm doing some traveling for the next couple of weeks. So, but for you guys, it's the same cadence. But yeah, I as you can still probably tell if you're watching on YouTube, I haven't got my desk set up. Still recording in my bed. Microphone in hand. But it's been a good time transitioning to Chicago. Um, and these podcast recordings and these conversations with experts in various industries, I feel like we've had a large variety over the past few weeks, which has been super cool. And for this conversation, we get into a topic that we have covered in the past, but with a twist. We talk about metal 3D printing or metal additive manufacturing. And our guest today really talks about not just the landscape of the space in general, but what his company is currently working on, where traditionally some methods are like selective laser melting, right, with powders, but their work focuses on ultrasonic energy and kind of uh single like or metal wires instead of powders, and it helps make things more cost effective, less post production, etc. So David, I just wanted to hear your thoughts on highlights for the episode that you found particularly interesting.
Yeah, I thought that it was really interesting because the technology seems pretty cutting edge to the point where a lot of some of the more technical aspects are like trade secrets. So we're really getting in on the ground floor here where he was able to tell us about kind of the process of how they thought of it, development, and then running it. But I thought the coolest part was when he was able to compare all of the different types of additive manufacturing and then really dive into why this new type of additive manufacturing works. And basically, we're just still heating up the metal just in different medias, and it allows for some really interesting ways to produce new parts. And so I thought that was a really interesting part of the episode.
For sure. And I thought it was interesting just hearing his perspective on manufacturing challenges that you face in the early stages of a startup company versus just generally what he envisions those challenges may be later on when manufacturing at a much larger scale, or what do larger companies, what kind of challenges do they face. And it was interesting hearing that perspective, especially I had an internship at GE, and so we were able to kind of learn a lot about the metal additive space from their end when they're manufacturing components, complex components for aircraft engines, right? And just hearing kind of a different perspective, how to make things potentially more cost effective, and just seeing that comparison as it stands right now. So there's a lot that we talked about today, and so we'll get right into it. But I just wanted to ask if you guys enjoy the episode, if you guys want to support the podcast, we would really appreciate if you could leave a rating and review on your favorite podcast platform. That would mean the world to us, and it would help push this podcast out to other material scientists and engineers who are passionate about the space. So, without further ado, let's get into it. Hello, everyone. For today's guest, I'm happy to welcome Dr. Anagh Deshpande. senior process engineer at a medical device company. Anagh earned his PhD in mechanical engineering from the University of Louisville. He also has entrepreneurial experience as he was the co-founder and principal engineer of Reverb Industrial, a company delivering a new additive manufacturing technology. He's an expert on metal additive manufacturing as well as manufacturing process improvement. So we're excited to dive into these individual areas. So thank you so much for agreeing to come on the show, Anagh. It's a pleasure having you.
Thank you. Thank you for having me.
Great. Yeah, so we wanted to really talk to you about metal additive printing. And so usually the spotlight on additive manufacturing is that of plastic material. How does metal printing compare to the familiar 3D printing of the plastic that we're so familiar with? Can you give us more detail to where the technology is compared to that of plastic 3D printing?
Yeah, definitely. So just to lay the groundwork, additive manufacturing or 3D printing, the terms can be used interchangeably, is building parts, components layer by layer. So you stack these layers, you fuse the layers together, and that's how you get a 3D geometry out of it. And as you mentioned, additive manufacturing can be broadly divided into plastic 3D printing and metal 3D printing. Metal 3D printing, or rather plastic 3D printing, is accessible. You can get a plastic 3D printer off of Amazon for a couple of $100. And then these printers range from anywhere between $200 to industrial grade plastic 3D printers up to even several $100,000 as well. But in general, plastic 3D printing is much more accessible. But if you look at the metal 3D printing side of things, the process physics of most metal 3D printing technologies is such that these technologies are not accessible or affordable, at least right now. If you were to purchase a metal 3D printer, it would cost you anywhere between several $100,000 to several $1 million. And that's just the equipment cost. You also require a lot of auxiliary equipment. You require changes to your setup, the place that you would put that equipment in also requires changes. And all of these costs add up. And so that's what makes metal 3D printing not so accessible right now. If we take an example of the most commonly used metal 3D printing technology, which is called laser powder bed fusion, some people call it SLM or selective laser melting as well. The idea behind the technology is you have a bed of powdered metal. A laser comes in, scans an area of that powder bed together and forms a solid metal layer. And then another layer of powder is placed on top of it. Again, the laser comes in, scans that layer, creates a solid layer of metal. You stack these layers together, and what you get in the end is your 3D geometry. So basically, you're using heat energy to create a melt pool of material. You're changing the metal from solid to liquid and then back to solid. This is also not very energy efficient because you're using a laser. Lasers are inherently inefficient in terms of energy conversion. And then you're also losing a lot of the heat to just conduction and to the environment. You have to take care that you have inert gas environment so that the metal doesn't oxidize. You also have to enclose all of it in a proper build volume. So all of these things make the setup very complicated. And that's one of the reasons why metal 3D printing is being widely used, but it isn't as accessible as we would like.
Interesting. So do you see us there being a future where it becomes similar to kind of like the plastic 3D printing where people can, cost reduce eventually there might be a smaller, more portable version for metal 3D printing? And if so, how much longer until we get to that point?
That's a very good question. And by making a prediction, I might put myself in trouble a bit, but still, I will take a shot at it. And I think this is also a good segue into talking about the technology that I worked on developing. So, as I mentioned earlier, the most commonly used metal printing technology uses heat energy to create a melt pool of material. It's energy efficient, energy inefficient, and not as cost effective or accessible. So what we wanted to do is move away from heat energy and see if we can achieve the same effect without using heat energy and stack layers of material. So first of all, start with deforming the material to the right geometry and then placing it at the right geometric location, and then fusing it with the material below it and adjacent to it, very similar to how you would do it with Lego blocks. So in a Lego set, you take a block of material, you place it at the right geometric location, and then you stack these Lego blocks to create a 3D printed, not a 3D printed object, but just a Lego toy. So if you look at 3D printing from a similar angle, then we wanted to see if we can deposit voxels of material, deform them to the right geometry, and then place them at the right geometric location, and then bond them to the lower layer and the adjacent material, and then place several of these voxels and create a 3D printed object. But we did not want to use heat energy for that. And then one way we realized we could achieve this is by using acoustic energy or ultrasonic energy. And ultrasonic energy or acoustic energy has a similar effect on metals, that it can lower the yield strength of metals so that you can make the metals deform at stresses much lower than the yield strength of the metal. And then it also allows for bonding of the material to the lower layer and the adjacent material. And the same reduction in flow stresses in the material that you can achieve with heat energy can be achieved with acoustic energy, but with a lot less input of acoustic energy. So then that process becomes much more energy efficient. And so we developed this technology which enables metal 3D printing to become a lot more accessible. And now you can have a printer that will give you a metal 3D printed component right off the printer, and you don't have to necessarily make any changes to your environment in which you put the printer. You do not need inert gas environment. What you get off the printer is your component. The power consumption is also significantly lesser. And so we are hoping that that technology makes metal 3D printing a lot more accessible, a lot more cost effective, and a lot more applicable as well, because it's now more accessible.
Could you maybe explain in a bit more detail? So you say that it can either help bond or lower the yield strength. So now instead of a bed of powder, are you using a like actual raw material, like a solid block of metal? That's question one. And then question two is how like exact can you use ultrasonic energy? Like a laser for me is very easy to imagine, like, oh, I just point a laser here and it's like a certain radius based off the laser grade. How exact is ultrasonic energy?
Yeah. So one thing to quickly mention is we use solid metal, but in a filament or a wire form. So we have a wire of material that gets deposited to print a 3D object. And then to go to the other part of your question, if you think about heat energy, it's vibration of atoms. So if you heat up a material, the atoms in the material start randomly vibrating. Ultrasonic energy is also vibration of atoms, but it's directional. And so what we have seen is it has similar effect on metals. As I mentioned, it lowers the yield strength of metals, and it also allows for fusion of metal. If you just think about it in terms of what heat energy does to metal, so if you heat up a rod of metal, it becomes easy to bend it. So because you have effectively lowered the yield strength of the material. Or if you heat up two blocks of metal and then press them against each other, eventually there will be diffusion across the interface, and then they will become one. If there is no, let's assume there are no oxides on the metals. If you just put them together, eventually there will be diffusion across the interface, and then it will be one block. Ultrasonic energy is similar. It allows for motion of defects. So all types of plastic deformation is motion of defects called dislocations. So the dislocations move, and that's what causes metals to deform. Or diffusion is again movement of defects, but in this case the defects are point defects called vacancies. So it's just missing atoms in an array of atoms, and that's the movement of defects is what causes fusion. And so just like heat energy, ultrasonic energy also enhances movement of defects, and then that allows us to use it for metal def and metal fusioning and bonding.
Interesting. So, how did you end up kind of getting into this space or, discovering kind of the use of ultrasonic energy versus heat energy, and what unique challenges did that alternative path present to you?
Yeah. So I have to be honest, when I got in additive manufacturing, I didn't really know what I was getting into. It sounded very cool. I completed my bachelor's degree in India in mechanical engineering, worked in India for 2 years, and then came to the US for my master's degree. I wanted to get some exposure to research, so I approached my advisor, Professor Keng Shu, at Arizona State University, and I just asked him if he had any projects I could work on in his lab. At that time, he had an idea of using ultrasonic energy slash acoustic energy for metal 3D printing. And it was just an idea in his head. Not much work had been put into it. So then I started working on that project under his guidance. So this project is, of course, his brainchild. And we started developing the understanding of interaction of ultrasonic energy with metals. And while we were developing that understanding, we kept applying that to this technology as well. So we wanted to understand how ultrasonic energy affects motion of defects, how the microstructure in the metal evolves when we irradiate the material with ultrasonic energy. And then all of this understanding then fed into development of this your additive manufacturing technology. And initially, when I got in, I was not in the mood to do a PhD. I did not want that. I just wanted to finish my master's, get a job. But then Professor Keng piqued my interest. He was the one who would make me curious about things. He would say things like, every now and then he would throw a nugget like, oh, if you had more time, you could explore this aspect as well. Oh, if you had more time, you could explore that aspect. And then that sort of roped me into doing a PhD. And so then I continued doing my PhD in his group. Then he moved to University of Louisville for a bit. So I moved with him, finished my PhD at the University of Louisville. But now Professor Shu is back at Arizona State and continues to develop this technology and help us understand this technology better. But that's how I got into it. And then the challenge was to not only develop this technology, but also to first develop a physics-based understanding of how ultrasonic energy interacts with metals, and then keep applying that to the development of this technology. So it wasn't just technology development; it was also pure science-based and developing an understanding of process physics and then applying it to an engineering problem.
Okay, well, I was just curious because I know you mentioned process physics and the background in process improvements as well. Maybe if you can give like just a high level overview of some of the manufacturing challenges that like early stage startup might face in this space, metal additive manufacturing, and how that might differ from the challenges commonly faced when producing at a much larger scale. And maybe you can tie it to your experience with Reverb Industrial, or maybe you can just speak on more of a higher level.
Yeah. So when we founded Reverb Industrial, the biggest challenge I felt was that, and I alluded to it a bit in my earlier answer as well, that we weren't just developing a technology, but we were also developing a physics-based understanding of it. And so and then that makes it also harder to manage. If you are working on a software startup, you can develop your technology, you can develop your product in 6 months to a year, and then launch it and then reiterate on your product. But because this was a science problem to begin with, the development cycle is much longer, and so managing that development cycle was was the biggest challenge for us. And then of course you also have finance related challenges where you're trying to raise money, but you also are developing the technology at the same time. I think on the technological development front, we did really well. We developed a technology that now allows us to have uh, a metal 3D printer that can print metal components using the technology. So, but on the financial aspect, things were difficult to manage as well. So that was more of a management related challenge rather than a technical challenge itself.
Interesting. So maybe we can dive into more specific use case of the technology. In a previous conversation, you mentioned that one of the key milestones for Reverb was providing proof of concept of this technology using aluminum 6061. Could you elaborate on why specifically that grade of aluminum and why it's important material with regards to compatibility with this technology?
Yeah. So when we started out, we provided a proof of concept with pure aluminum. Pure aluminum, as you might know, is what we call an FC metal, face-centered cubic metal. Because of this crystal structure, it's softer, it's easier to deform it, and other FCC materials are also metals are also similar. Copper is one example, gold is another example. These metals are easier to deform, so they're easier to work with. So it was the lowest hanging fruit for us to provide a proof of concept for that. But now, if you think about the activity of pure aluminum, it's not used anywhere. So anywhere you require structural components which have decent strength, you would have to use an alloy. And 6061 is one of the most commonly used alloys. So in order to achieve the strength, we add alloying elements to aluminum. And then these alloying elements form what we call precision. And as I mentioned in my earlier answer, we are relying on motion of defects for deformation and for diffusion. But now you have these precipitates in your alloy which are hindering the motion of these defects. So they are basically like roadblocks or barriers for the motion. And it was important to overcome this technical challenge so that our technology could be applied to aluminum 6061 as well, because that would mean that our technology can be used to print structural components as well made out of aluminum 6061, not just these pure aluminum, pure copper, gold components that are not applicable to structural applications. And so that was the challenge. How we solved it is trade secret. We're publishing a paper on it very soon, so you'll be able to read more about this in that paper. But in general, in order to achieve printing of aluminum 6061 with our technology, we essentially had to increase somehow the motion of defects and then achieve plastic deformation and also diffusion and hence fusioning of the material.
Got it. So since I can't ask, since it is a trade secret, I just want to speak on or take a step back and ask when you talk about the development cycles, was your focus at that time just purely aluminum 6061, after just pure aluminum, or were you thinking of and considering other materials as well and looking into how other metals or alloys could potentially be compatible with this ultrasonic energy technology?
Yeah, so we did primarily focus on 6061, but we also knew that once we provided a proof of concept for 6061 and once we narrowed down the process parameters for 6061, we would be able to more seamlessly develop other aluminum alloys, of course, but also some other materials. We haven't gotten to that point yet where we have developed other materials, but that work is also underway. And Professor Shu's lab at Arizona State University is continuing the development uh, of the technology with other materials, and not just aluminum and aluminum alloys, but also to other materials like copper, which has applications in heat exchangers and stuff like that.
So maybe going back to a previous question Puneet asked. So when you were first starting up this development cycle, you talked first about like the defect. So that's one large technical issue you had to overcome. As you scale it up to a more mature process, what other issues do you anticipate to face when you are working on it? Potentially on the size of the size of the material that you can do, or maybe even like the speed at which you can print?
Yeah, that's a very good question. It's one thing to print one component and just say that we have a proof of concept for it. And it's another thing to reliably keep printing components, not just on one machine, but several machines. So you're not looking at just reliability of one machine, but you're looking at reliability across machines. And that is a very tricky engineering problem, which we are still working on. But to just talk about how we try to solve it, in the end it comes down to narrowing down your process parameters and just performing experiments after experiments to zone in on the process parameters. But then that can only take you so far. In the end, what you have to have is also a physics-based understanding of the process, so that when you're tuning the process parameters, what's happening in the material. And once you have that understanding, then narrowing down the process parameters becomes slightly easier. Did that answer your question, or was
Yeah, no, I think, yeah, definitely any step of a process is simplifying it, trying to create like a controlled process. I guess maybe as we look to iterations of next development, what challenge do you think will pop its head up first? So now that you have proof of concept, of course, the challenge is to scale it up. One is quality. What other challenges are you guys working on to scale up to a more repeatable process over multiple tools?
yes, sorry. I will also go back a bit to your previous question about the size of the components and the
Sure.
scaling of the process, and then tie it up to your current question. So, yes, in general, additive manufacturing processes are slower. And so printing bigger components with these processes is time consuming. And I think that is one of the hindrances in adoption of additive manufacturing technologies. In our process, there is nothing in the process physics that stops us from scaling the technology. And we have also thought about, well, one is we can use bigger feedstock, but then if we use bigger feedstock, that compromises the resolution of the process. And so that is the trade off, and that is the challenge that we are trying to also work on, is how do we address this trade off of printing faster, but if we do that, we compromise the resolution of the process. So we are trying to balance this trade off and also trying to make our process faster, but at the same time not having to compromise the resolution.
Yeah.
And then there are some trade secrets there that we are working on that hopefully help us solve this problem.
Yeah, so maybe not to step in on your trade secret, but just a rough idea. With 3D plastic printing, I think we all know like generally how fast it is. For metal printing, maybe could you describe like how fast the standard metal printing is, and then how fast your method of metal
Hmm.
printing would be, and compare the three?
So if you look at metal 3D printing in comparison to plastic 3D printing, I don't know if it would be an apples to apples comparison, but I would say they are comparable. There is, of course, a lot of setup time that goes into setting up a metal 3D printer before you can hit that print button and then it starts printing. But if the baseline is that the printer is set up, then plastic 3D printing and metal 3D printing, some metal 3D printing technologies at least, are can achieve those speeds of plastic 3D printing. Our technology right now, at least, is on the slower side. So the technology can print metal components. I'm trying to think if I should quote a number here, but I'll refrain. And I'll just say that our technology is on the slower side.
So, how generally, how do you go about, like, pitching this to, potential, like, investors or potential clients as well? Like, what is the advantages? I know you mentioned from efficiency standpoint, But when you're competing against larger companies who have invested millions and millions of dollars into improving this technology and kind of producing at scale, let's say like for instance, with their, their metal additive space, how do you kind of find your niche? What exactly are you conveying to potential investors? It's like, here are the advantages of this technology versus what we see traditionally in the metal additive industry.
Right. So the first thing that we want to convey is that our technology, like I mentioned, is cost effective and accessible. What you get off the printer is your final component. You do not require any post processing operations. You can choose to perform them and make the parts surface finish better and stuff like that, but you do not require it. That's one thing. The second thing is that because the technology does not require you to make elaborate changes to your setup environment, that's a significant advantage that allows companies or also small and medium scale manufacturers to now take advantage of metal 3D printing. Because if you look at metal 3D printing landscape right now, that technology is accessible only to bigger companies. So small and medium scale manufacturers have not been able to access the technology. But hopefully with this technology and the improvements that we are making to it and the development work that's happening in Professor Shu's lab at Arizona State University, we will get it to a point where small and medium scale manufacturers will also be able to access it and will not have to spend as much capital in installing it and then just utilizing it.
Yeah. So we've had one other person before talk about metal printing. One of the big things is like the waste powder. So like you're talking about for SLS, you make like a huge bed of powder, and a lot of the powder goes unused. I guess with that in mind, is there like significant cost savings theoretically for this type of process? And then, like you said, the cleanup is much easier.
Yes. So one advantage with our technology is, well, not using powder at all, because once you use powder, especially for metals like aluminum, that powder is flammable. So you have to have a certain type of fire safety system in your building. Your usual fire safety system with sprinklers doesn't always work. So you have to overhaul that to install a printer that can print aluminum powder essentially. So we don't use aluminum powder, we use fine filament. So that problem is gone. And yes, there is much less wastage of powder itself. And the cost of raw material is also lesser than what you would have to pay for powder. Because now we are using wire or filament. We are not using powders at all.
Awesome. Appreciate the overview of this space as well as this like unique technology. I'd honestly never heard of it before, so it was really cool to kind of hear like, because I've had an internship at GE, and so just, we heard about it from the traditional metal additive side, and to hear kind of an alternative path to accomplishing a similar goal, perhaps in a more cost-effective way, was very intriguing. And so maybe to wrap up the conversation, we would love to just get your advice on how students who are interested in additive manufacturing can stay involved, stay updated in this industry, and continue to improve their skills when it comes to process improvements and manufacturing efficiency and things of that nature.
Yeah, my advice would be that if you are an undergraduate student and if you want to get into additive manufacturing, see if you can find a lab in your university that's working on additive manufacturing related problems. The great thing about additive manufacturing is that it's not just limited to material science or some field of engineering. Additive manufacturing involves material science, mechanical engineering, material characterization, physics, and all of these fields combine together to form additive manufacturing. And so the good thing is that you can choose your gateway into additive manufacturing. You can approach it from mechanical engineering aspect, you can approach it from material science aspect. And so most departments in universities these days, most engineering departments in universities these days will have labs that are working on some sort of additive manufacturing challenge. I think that is the best gateway to get into additive manufacturing, and then you can also decide whether you like that aspect or if you want to explore some other aspect of additive manufacturing. So yeah, that would be my suggestion.
Yeah, I appreciate that. I think David and I followed similar paths where we got involved in research and then we kind of leveraged that experience to get internships as well and just see both sides of the same coin and then continue to explore other industries or go back to the same one. So really appreciate that advice. And again, thank you so much for joining us today, Anug. It was a pleasure having you, and we're excited to stay in touch and continue to see your technology grow in the metal additive manufacturing space.
Awesome. Thank you so much. I enjoyed the conversation, and yes, I hope to stay in touch.
For sure. As a materials engineer, we can make an impact in nearly every single industry. But with that versatility comes a lot of different options to choose from. So if you have no idea which industry or position is right for you, believe me, you're not alone. I've been there, done that. But just for a moment, imagine narrowing down your ideal role and company by the end of this week. Imagine being able to secure your dream job offer without having to apply to hundreds of job openings. Our online course, MSE Academy, includes video testimonials, resumes, interview prep, and mentorship from materials engineers who have been in your shoes. We also connect our members with companies and industry professionals in our expansive network to help accelerate your job search as much as possible. To learn more and get started, simply click the link in the description below. And if you enroll within the next 24 hours, we'll add 3 bonus career development resources. I hope to see you there.